Okay, so this is the continuation of lecture 9. So in this lecture or this part of the lecture, I want to talk about ray tracing. So for ray tracing, we're thinking of light as a beam, and we're thinking of it traveling in a straight line unless it encounters a surface. And then that surface could either create a reflected beam or a refracted beam in the manner that we discussed previously. So the process of ray tracing is really to use those principles to understand the reflection and refraction of light and interpret images that we see from reflective surfaces and translucent surfaces, right? Okay, so we're going to begin with just flat surfaces because it's a lot easier to do this with flat surfaces before we talk about curved surfaces. So we'll start with just a plain mirror. And the idea behind ray tracing is that obviously we have light sources like the sun or light bulb. Light bounces off of objects in all directions. And so we can think of any object as itself a source of light, right? It's maybe not an origin of light, but it could be a source of reflected light, right? So I want to think about the light coming off of an object. So here I just have an object at a point that the light is coming off in all directions, and whatever happens, the light travels in a straight line until it encounters this reflective mirror, and then the light obeys the law of reflection, which says that this angle of incidence is equal to the angle of reflection. Okay, so how can we use this to understand what's happening in a mirror? So in a mirror, I have, let's say, an object in this position, but maybe I'm looking at the object as a person over here, right? So the light is bouncing off of the object, reflecting off of the mirror, and then coming over to me in this position. But what would my eye interpret the light doing? So my eye doesn't understand the law of reflection. My eye interprets light to travel in a straight line, right? And so my impression is that there's a virtual object or an image that is in the position located here, right? So we would call this point P, what is that called? P prime. It took me a while. Okay, so P prime is the image of the object at P, right? So if the object P is a distance S away from the mirror, then P prime is a distance S prime from the mirror, okay? So now we can use some geometry, right? So I know that if I have these two intersecting lines, so the line of the mirror and then the line of this real ray and this virtual ray, I can tell that this angle theta r is equal to this angle theta r. But because of the law of reflection, I know that this angle theta r is also equal to this angle theta I, right? And so it'll turn out that this triangle is an identical triangle to this triangle, and therefore this distance S has to be equal to this distance S prime. And so what do you see when you look in the mirror? You see an object or an image of yourself that is the same distance away from the mirror as you are from the mirror. Okay, so the law of reflection gives the angle of the reflected ray, which is a straight line to the image, right? So there's a straight line from the reflected ray to this image that is behind the mirror. So you could do this with not just one beam of light, but several beams of light, and show that actually your eye would interpret that there is a virtual image that looks identical to the object that is in front of the mirror. So here's kind of a neat trick how you could use a mirror to help you play pool. So here, if you put a mirror in this location, in the back of this pool table, then you would aim the ball directly into the socket in the mirror, and you would expect to see, what would really happen is that the ball would be reflected off of the back of the pool table and then hit the real image of the real socket in this corner. So pretty neat use of the law of reflection. Okay, so there's actually a principle of ray tracing that if images are formed at the intersection of virtual light rays, so here virtual light rays are any of the imaginary light rays that I'm drawing behind the mirror. So I know that there aren't any real light rays behind the mirror, and so therefore the intersection of these lines is at a virtual image. If, however, I have light rays intersecting in front of the mirror, that would be the creation of a real image. So it is possible to make a real image as opposed to a virtual image. Well, we're going to see the distinction between the two later on once we look at lenses and curved mirrors. So here the image is made by backtracking, right? So I want to continue these light rays behind the mirror, and therefore this is a virtual image. Okay, this is one of my favorite problems to do with ray tracing. So it's saying that I have a man standing in front of a mirror. So you are that man or woman. You are 1.6 meters tall, and you want to be able to see your full image in a vertical plane mirror. So it's asking, what is the minimum height of a mirror that will meet your needs, and where should you place that mirror, right? So the idea is I want to know what is the shortest mirror that I can use to see my entire body, and where should I place that mirror in relation to my body. Okay, so maybe you want to think about this and draw a couple diagrams to try to decide what the best use of this mirror is and how long it should be. Okay, so go ahead and pause and think about this. If you're coming back now, then let's discuss this principle. Okay, so the idea here is that I have a person who's 162 centimeters tall. The eyes are, let's see. So it says that my eyes are 14 centimeters above my eye level, right? And so that means that my eyes are, let's see how tall. My eyes are 1.48 centimeters above the ground, right? So if I want light to basically bounce off of my toes and hit a mirror and then come back to me, to my eyes, then I need to place the bottom of the mirror at exactly halfway the distance between my eyes and the floor, right? So if my eyes are at 1.48 centimeters or 148 centimeters off the ground, then the bottom of the mirror has to be half that distance above the floor. So 74 centimeters above the floor. 148 divided by 2 is 74. And then where would the top of the mirror need to be? So the same process, right? So light has to bounce off of the top of my head and then hit the top end of the mirror and then reach my eyes, right? So that would mean that the top of the mirror needs to be halfway up between my eyes and my forehead. Right? So that means that I need the top of the mirror to be here, or 7 centimeters from the top of my head, right? So the top of my head is at 162 centimeters, so that means 162 minus 7, this needs to be 155 centimeters above the floor. And the total length of the mirror needs to be half my height, right? So 81 centimeters tall, right? So here's a really interesting question. Does it matter how close you are to this mirror? And the answer to that is no, right? There's no distinction made for how close you are to the mirror, only how high up this mirror needs to be positioned so that you can see the bottom of your feet in the bottom of the mirror and the top of your head in the top of the mirror. So isn't that interesting that it wouldn't matter even how close you are to the mirror? Okay, maybe you want to think about this and draw some diagrams yourself, right? So then actually the best way to see this happening is to draw the image of the person, or the person on one side of the mirror, and then the virtual image on the other side over here. So draw 2 people that are identical and looking at each other. And then you want light rays going from the bottom of the feet of the image all the way to the eye, and then light rays going from the top of the image of the person all the way to the eye, right? So these would be the virtual light rays that extend behind the mirror. And that would be what the eyeball interprets to be happening to the light. So the eyeball interprets that light is traveling in a straight line from the bottom of the feet of the person to the eye, to the top of the feet of the person to the eye, right? But what's really happening is that light is bouncing off of the person and then coming back to the eye. Cool. Okay. Here's another question. It says, a fisherman looks directly underwater at a fish. From his viewpoint, does the fish below appear to be further below the surface, closer to the surface, or at the same distance from the surface than it actually is? So maybe you want to draw a picture and figure out what this should look like. Or maybe you can imagine it happening in real life. Okay, so if you're coming back, let's draw a diagram of what this looks like. And this is actually a picture that I showed in the previous part of the lecture. So here I have not a fish, but a scuba diver, and it's underwater. And then this is the person above the water that's looking down at the scuba diver. So notice that light is bending towards the normal, right? So if light is coming from the scuba diver to the lifeguard, then as it's going from the slow, medium to the fast, it's moving away from the normal. And so that explains the path of light that's going between the lifeguard and the scuba diver. So again, the eyes of the lifeguard don't know how to interpret the bending of the light, and so what's visualized is light traveling in a straight line, right? And so that would mean that there would be a virtual image here in a location that is closer to the top surface of the water, right? So this is what would happen with the fisherman. And the fish would appear to be closer to the surface, right? And then, so the alternative question is, what would the fish see if it looked up at the fisherman? It would see that the fisherman is higher above the surface than he really is, right? So another thing that would happen is that you would visualize the edge of the pool being closer to you than it really is. Okay, so here's some more demonstrations of refracted images. So this is a mirage. So if you've ever heard of people saying that in the desert it looks like they see water in the distance, but it's not actually there. So the reason for this is the bending of light that happens when the air above the surface of the ground is very hot. So it's going to cause light to bend here. So this is kind of demonstrating light bouncing off of the of this truck and bending before it reaches the person in the car. And so the car would interpret this as being light that's coming from below the surface of the ground, but inverted, right? So instead of seeing the truck ahead of you, you would actually see an upside down truck underground that's coming towards you. It seems kind of freaky. So what's happening actually with this mirage is that you're not seeing directly ahead, you're actually seeing the sky, and the image of the sky is actually bending towards you, and so it looks like there's water on the ground when there really isn't. Here's another application of this happening. So whenever you're looking at the sunset, the sun is actually in a different location relative to the earth than what it really is, and it's because of the bending of light in the atmosphere. So you would see light bending towards you when it goes towards the observer, so the apparent position of the sun is actually higher up than it really is. Okay, I'm just gonna pause for a second. Okay, I'm back. So I just want to show this neat GIF. It's showing an anglerfish. So the way anglerfishes catch their prey is by spitting at them. And this is just, to demonstrate, that it's kind of a matter of two kinds of refracted things. So if you think about the position of the prey for the anglerfish, he has to think about the light bending when it impacts the surface of this water. But if you're also thinking about the ballistics of actual things being fired, so he's spitting, that spitting also has, has the impact of gravity on it, but also if he's spitting underwater, there's, some refraction happening for the actual spit, let's say. So lots of interesting things happening in conjunction with each other. The reason why I mention this is I think when submarines shoot cannons or whatever, shoot whatever missiles, they have to consider the refraction of the missile when it goes from water to air. Right, so a similar thing would happen for refraction even with solid objects, right? Not just light. Okay, let's continue. This is one of my favorite things to talk about for optics. So this is called a camera obscura. So I'm moving my picture over to this side. So camera obscura, it's really simple. So here I have a room, and there's a small hole. And what's going to happen is the image of this person is actually going to get projected onto the wall of the room. And so think about this light ray from the head going through point C, and then the image from the foot is actually also going through point C. So it actually flips upside down and gets projected onto the wall. And so this is the wall of some, cathedral, I think, in Italy that has a camera obscura, and you can actually see the image of what's happening outside projected upside down on the wall of the cathedral. So something similar happens during an eclipse. So hopefully everybody got to see at least a partial eclipse a couple of years ago. I don't remember exactly. I think it was 2017 in the summertime. There was an eclipse. I actually got to see the total solar eclipse because I went down to Nashville, where there was, a really perfect solar eclipse. Anyway, so what happens in a solar eclipse is that light traveling, in between the leaves actually gets projected onto the ground. And so each hole between leaves becomes its own little camera obscura, and you can actually visualize what's happening to the sun because it's being projected onto the ground. Right? So that's what all of these little crescents on the ground represent. They're all images of the sun being projected onto the ground. So one use for this actually is people use this box to project an image of what's happening in front of the box onto the top of a screen, and then they use it to sketch out the outline of what's going on, and they can use this as like a starting point for a drawing. Right, so you could use this to kind of represent, a very primitive camera. Okay, this actually is a really cool website that I found, or a blog post, and it's how to convert your room into a giant camera obscura. And it's very simple. You just have to block out all of the light, so cover the windows, and then poke a tiny hole in that blocked out light, and it will project an image of everything that's outside of your window onto the walls of your room. Okay, so next thing to talk about is dispersion. So dispersion is really another way to talk about, or it's maybe a formal word that just means the principle behind how rainbows are made. So let's talk about what happens during dispersion and why it happens. So we know that, this is a cute cartoon. I'll just skip through this. So we know that that light travels slower through transparent media than it does in air. But what we haven't mentioned is that index of refraction that represents how much slower light travels, that it's dependent on frequency. So it turns out that blue light will travel slower through a prism than red light, right? And one way to represent this is by saying that the index of refraction in the red frequencies is smaller than the index of refraction in the blue. Right, so I could actually have a plot of index of refraction as a function of wavelength, right? And so we see that n in the red wavelengths is actually smaller than n in blue. It's smaller by a very small amount, right? So here these are two different glass. Here it's starting off at 1.6 and ending up at 1.58, right? So there's a very small distinction between it, but there is a lower index of refraction as you move to higher wavelength, right? Or lower, or higher wavelength is smaller frequencies, right? Okay. Okay, so now that we know that n is different when we're in glass, we also know that Snell's law determines the angle of refraction. And so if n is bigger for blue light, that means the angle that blue light gets deflected is bigger than the angle that red light gets deflected. So we see two positions where this happens. The red light actually bends the least, whereas the blue light bends the most, right? And we end up going from light that it has all wavelengths, so white light has all wavelengths in it, when it travels through this prism, the different frequencies of light get separated from each other. And that's what dispersion means, right? It means to separate out. And in this case, we're separating out the different frequencies. Okay. This is a picture of a double rainbow, and this is a picture that I took out of my window, and it was immediately after the first time I ever gave a lecture about rainbows. So something really magical. One of the highlights of my teaching is when this happened, is that I taught a lecture about rainbows, and then I came back to my office and I looked out the window and there was a double rainbow. So you can see this is the primary arc of the rainbow, and this is the secondary arc. Okay, so let's talk about rainbows, but before we do that, I want to just talk through the process of what's happening for a triangular prism. So here I have this is my incident ray, this initial line. So I start off with this incident ray. The angle of incidence I'm calling I, and the angle of refraction I'm calling R. So here I'm going from air to glass, and so I'm bending towards the normal. And then what's going to happen at this second interface, I'm going to go from glass to air, so I would expect to bend away from the normal, right? So essentially I have this is angle I, this is angle R. If this prism is symmetric, then this angle R is equal to this angle R, which means that this angle I would be equal to this angle I, right? So we end up with the same angle on either side. And so that's why this incident ray comes out at a symmetric angle I. Okay, so how would I represent how much the light has been deflected by this prism? So I want to find the difference in angle between the incident ray and the outgoing ray. So that would be this angle. So how much is the angle, how much is the light deflected initially? It's deflected an angle delta 1. How much is it deflected in this second interface, it's deflected an angle delta 2. And so the total angle of deflection, delta, would be the sum of these two deflections, delta 1 and delta 2. Right, and this angle would tell me the difference between the incident ray and the outgoing ray. Okay, so I only wanted to do the triangular prism because now I want to talk about what happens for a circular prism. Because for a circular prism, it's mimicking what's happening in a cloud, right? So a cloud has a bunch of droplets of water. Each droplet of water is its own prism that's creating the rainbow. So let's also look at what's happening for blue light. So we know that blue light is going to bend more than red. And so here I have blue light that bends more than red at both interfaces. So here it's bending more than red, and here it's bending more than the red light. And so I would expect the angle of deflection of the red light to be smaller than the total angle of deflection of the blue light. Okay, so now let's do a circular prism or a raindrop, right? So I'm going to start off with light coming in over here on top, and then what's going to happen is I'm going to have bending towards the normal, and then I'm going to reflect off of the back of this raindrop, right? So I could actually have light escaping off of the back, but let's imagine that I have light reflecting off of the back and then also refracting again, right? So imagine this is sunlight coming in from the top, bending, reflecting, and then bending again. So how could I come up with the total angle of deflection for this raindrop? So I would take the difference between the incident ray, so this is the incident ray, and the outgoing ray is this this line here. So that angle is here. So this angle here, and delta deviation, that's how much the light has bent. And if I take 180 minus this delta deviation, that gives me delta rainbow. So it turns out that I can also calculate what happens for blue light. So blue light is going to bend a little bit more, reflect off of the back again, and then bend a little more. And so now I have a deviation or rainbow angle for red light and rainbow angle for blue light. It turns out that these angles could be anything, any angles, but the angles are maximized for particular angles. Sorry, the intensity of light that comes out of the raindrop is maximized for a particular angle, and it has a different particular angle for different frequencies. So this actually is demonstrating what's going on. So I could have light coming in at all of these locations, and then I have refraction, reflection, refraction happening. But it turns out that there's an angle where a lot of the light rays are kind of piled onto each other, and so the maximum angle for red light turns out to be 42 degrees. For blue light turns out to be 40 degrees. And this difference in the maximum angle actually gives me the arc of the rainbow. So let's see why that happens. Oh, sorry. But before we do that, I want to talk about double rainbows a little bit. So here I just have the YouTube video of the guy who's like freaking out about a double rainbow. I don't have to show it right now. You've probably seen it before. And also I think that I can't show it. So let's just move on here to what's happening in a double rainbow, or the secondary arc. So for the secondary arc, I have light coming in from the bottom. It's going to reflect again off of the back of the raindrop, and then reflect again, and then refract, and then reflect, right? So here's the process. So it has a refraction, reflection, reflection, refraction, and then it comes back out. And then the angle between the incident ray and the outgoing ray ends up being 52 degrees for red and 54 degrees for blue, right? So it's actually the opposite. So if you remember, for red, the primary maximum angle is 40 degrees, and for blue it's 42. Or is it the other way around? It's 42 for blue and 40 for red. No, it's the other way around. 42 for red, 40 for blue. And here it's the other way around. Red is the bigger angle and blue, sorry, is the smaller angle, and blue is the bigger angle in the secondary arc. Okay, so what are these angles, and why do they make a rainbow? And so imagine you are at a particular location and the light is coming from behind your head, right? So it really only works when it's late in the day. So light is shining at an angle, or actually it could be early in the day too. So light is shining at an angle. It's reflecting off of clouds that are in front of you. And then at every position in that cloud, representing an angle of 42 degrees away from you, you would see a red arc. At 40 degrees from you, you would see the blue arc, right? So that would tell you where, how the order of the rainbow in the primary arc is blue to red. The order of the rainbow in the secondary arc is actually red to blue. So these are some more pictures of what's happening in a rainbow. And actually this diagram actually shows how you could figure out this angle of the rainbow. So you have sunlight coming from behind you, and you put a pencil or something up against a piece of paper. You could use that to measure the angle of the light coming in, because it would cast a shadow on that pencil in the direction of that light. And then you position the top of the paper in the direction that it points towards the top of the rainbow. So you could measure this angle that the rainbow makes according to the shadow of the pencil on your paper. Okay, so I just wanted to include some pictures of how rainbows can be explained. Okay, these are other pictures of interesting things that happen, optical effects, optical illusions that happen in the atmosphere. This one is maybe something you've heard of. It's called the green flash, and it's after the sun sets over the water, you might see a flash of green. These things are called sundogs, right? So I think they happen more often in colder climates. Here's a rainbow, creating a halo in front of someone's head. So I forget actually what they're called, but I've seen some of these things. I did want to also say that in addition to the secondary arc of a rainbow, you could actually have higher order reflections off of light, and so this would explain what it would look like to have 3 reflections, 4 reflections, 5 reflections, 6, right? So it is technically possible. However, every time you have a reflection off of the back of a raindrop, you lose some of the intensity, right? And so that's why it's really more common to see just normal rainbows and maybe also the secondary arc of a rainbow. Okay. So now we're done with rainbows. Let's talk about images created by lenses, right? So for this, we want to understand how glasses work, how microscopes work, things like that, how the lens in your eye focuses so that we can see. So lots of great applications of understanding lenses. Okay, so we want to categorize lenses into two different types. So one would be converging lenses. The second would be diverging. So a converging lens takes light that comes in parallel and bends light to focus at a particular point, right? So this is a converging lens because light that's coming in parallel converges onto a point. This is a diverging lens. So a diverging lens actually takes light that's parallel and causes it to bend away from the axis of the lens. So notice the actual shape of the lens is different. So here I have a converging lens is fatter in the middle, a diverging lens is skinnier in the middle. So in terms of concave and convex, I would say that this is a double convex lens. This is a double concave lens. And you could actually have lenses that are either flat on one side or both convex, concave. So there are other alternatives for converging and diverging lenses. Let's talk about focal length. So notice how before we had light coming in from the left that was parallel. So to find the focal length would be the distance from the lens to the point where all of the light rays converge. Right? So how would you have defined the focal length for a diverging lens? You would actually take these rays of light that come in out of the lens, right? So these light beams that go outwards away from the axis of the lens, we would trace them backwards behind the lens, sort of like we were doing with those virtual images. And wherever these light beams intersect, that would tell us the focal length of this diverging lens. Okay, so now we want to learn how do we use ray diagrams to draw images created by an object. So beginning with the object, remember we want to imagine that objects are themselves sources of light, and that could be true even if they aren't creating light, they are reflecting light in all directions, right? So we'll have a certain set of rules about how light beams pass through a lens, and then wherever these light beams converge back together, we'll be able to demonstrate that that is the position of an image, right? So we'll create real images where real light rays bend and cross together. We'll create imaginary images by extending light rays to see where it seems like the image would be, or seems like the image would be created. So we'll see examples of both real and imaginary images. Okay, so now I'm going to tell you the rules for light rays. And so there's three rules for lenses. In terms of both converging and diverging lenses, anytime you have a light beam going through the center of the lens, it's not going to bend. It's going to continue as if there was no lens. Right? So anytime you draw a light beam that goes through the center, it's going to continue straight ahead. And that's true for both converging and diverging lenses. Okay, rays that pass through a focal point become parallel to the principal axis. So let's see here, if I have a light beam that goes through the focal point of this lens, then I would expect that on the other side of the lens, it would come out parallel. And I should have mentioned, even with this process, right, we're still expecting light to bend every time it goes from one medium to another. But in this aspect, you would expect that it would bend and then bend back. And so the ultimate result of going through the center of the lens is that the light beams are not bent. Likewise here, we would expect light to bend on both the front and the back of the lens. However, we know that if if this is a symmetrically, convex lens, then the focal length actually is represented on both sides of this lens, and so we know that light coming from this focal point will actually bend to become parallel on the other side of the lens. So for a diverging lens, light that looks as if it's going towards the other side, the far focal point, will actually come out parallel. So the near focal point will be the focal point on the side of the incident ray. The far focal point will be the focal point on the outgoing side. Here, I have light coming from the near focal point, bending to become parallel. Here I have light that looks as if it's going towards the far focal point, and it comes out parallel. Okay, so rule number 3 is that for light rays that come in parallel, they will go towards a focal point. So here I have light rays that are coming in parallel to the converging lens, and so they will bend towards this focal point here. This is how we first described what a focal point is. And then for the diverging lens, I have light coming in parallel, but it goes outwards as if it came from the near focal point, right? So I'm going to go, whenever I draw a light beam, I'm going to hit the side of this lens, and then I backtrace back to the near focal point and extend a line that goes outwards. And so the light that comes out on the other side of the lens, all of these light beams look as if they came from the near focal point. Okay, so let's continue. And now we can draw ray diagrams. And this is actually what maybe the most typical ray diagram looks like. So here I have a lens, and I have an object. So here I have a Christmas tree, right? And so what's going to happen to the light, we can say it in terms of 3 light rays. So we're going to use 3 light rays. Here it's called special rays. And we're going to make every ray originate at the top of the Christmas tree. Why do we want to use the top of the Christmas tree? It's because essentially there's light coming from all locations on the tree, but if we use the top of the tree, we'll know how to identify the top of the tree on the image. Okay, and so now let's draw each special ray according to the rules that we described before. So here I have a light beam that is starting out parallel to the principal axis. It should go through the far focal point and continue on. Rule number 1 was any beam that goes through the center of the lens has to go through without bending, right? And then one of the other rules was if you go through the near focal point, you have to come out parallel, right? So now we draw these 3 special rays, we bend them according to the rules. We would end up getting an image at this location here, right? So even though there are many rays coming from the image in all directions from each point on the image, it really is enough to just use the top of the image and only these 3 special rays. Wherever the 3 special rays intersect together on the other side of the lens, that would be the location of the top of the image of the tree. Okay? So this is what the ray diagram would look like whenever I have the object outside the focal point, outside the near focal point. But what's going to happen if I move that object inside the near focal point? So what if this Christmas tree was actually in front of the near focal point? So now let's draw those 3 special rays again. So now I need a parallel beam. It's going to go through the far focal point. A beam that goes through the center continues out without bending. And then here I have a light beam. It can't go through the near focal point, but I could find the beam that looks like it came from the near focal point, and that beam needs to come out parallel. Okay, so notice how these 3 beams all splay out and diverge. And so how would I find the image? There's never going to be an image on this side of the lens. But what I can do is I can extend these lines backwards, right? So I can extend them backwards to this point where I have a virtual image. Wherever they intersect, that'll be the location of the virtual image. So notice that really different effects happened. In this situation, I have a real image made by real light beams, and it is inverted. It also looks smaller, right? So it's a shrunken, inverted, real image. What happens here, I have an enlarged, upright, virtual image, right? So here I have an inverted, real, shrunken image. Here I have an upright, virtual, enlarged image. So how could you see this virtual image? So if my eye was actually on this side of the lens, I would not be able to see the object. What I would see is this image, right? So this is the principle behind a magnifying glass, right? So when you put a magnifying glass in front of your eye and you look at some text, the text looks enlarged. It also looks like it's further away than it actually is. And that's exactly what's happening here, right? So you have to be on this side of the lens in order to view an object that is in front of you. And you see a virtual image that is enlarged and upright. Okay, so how do we figure out the location of these images? So luckily we don't have to draw the diagram in order to find the location of the image. We actually have a formula that finds it for us. And so that's good because then we can do it with algebraically and with a diagram and make sure that our answers agree. So in order to do this, we need to identify the different components of this. So I have the focal length represented by the letter F. In this case, the focal length, right, is equal on either side of the lens because the lens is symmetric on either side. And then I need an object distance. So the object distance would be the distance from the object to the lens. And then I also need an image distance. So that's the distance from the image to the lens. In this case, all three variables would be positive, right? So here, same deal. I have a focal length on either side of the lens. The image distance, this is actually opposite. I'm going to skip this here because I think I labeled this incorrectly. The object distance is actually this shorter distance. The image distance is the longer distance. So here's a bunch of rules. We want to draw an axis anytime we're practicing these ray diagrams. We want to represent an object with an upright arrow, a distance with an object distance DO, and an object height HO. We want to draw the three special rays and obey the three rules of what happens to rays, and then extend the rays until they converge, and that would be the image point. We can measure the image distance and the image height, right? So here I have ray diagrams for diverging lenses. So I'm not going to go through these right here, only to say that anytime you have a diverging lens, you would expect to see the image behind the lens, in front of the lens, right? Or on the same side of the lens as the object. So sort of the same thing that happened here for the converging lens, where the object was in front of the focal point. So the same thing happens for the diverging lens, regardless of whether the object is in front or in back of the focal point. Okay. So here's an equation. It's called the lens maker's equation. I like this, the title of this equation, because it basically it tells you how you could make a lens with a particular focal point. So here the R represents the radius of curvature of the lenses, and typically you would want these to have equal in magnitude radiuses, right? So it's telling you like how, what is the curvature of each lens. So R1 would be the side closest to the object, R2 would be the side furthest from the object. R is always greater than 0 if the lens side is convex towards the object, and then R is less than 0 if the lens side is concave towards the object. And so I think it'll turn out that when it's symmetric and these radii are equal, this doesn't equal 0, it's actually equal to 2 divided by R. N would be the index of refraction of the lens, the material of the lens, and then F is the focal length. Okay, here is the magnification equation. So this is really interesting. It tells you that the ratio in the image distance to the object distance is actually equal to the ratio of the image height to the object height. Whenever M is positive, that would give an upright image. Whenever M is negative, that would give an inverted image, right? Because then the image height would be negative. because the height is measured relative to this axis, right? So an image that is pointing down would have a negative image height. Okay, and this is actually the most important equation. It's called the thin lens equation. So this is relating focal length, object distance, and image distance to each other. Here's some rules about image distances and object distances. So for a converging lens, the focal length will always be positive. For a diverging lens, the focal length will always be negative, right? Object distance, I think, will always be positive, but image distance can be negative, right? So remember that the image can either be behind the lens or in front of the lens relative to the side of the incident rays. And so if you have the situation of the image distance being on the same side, the image on the same side as the object, that makes the image distance negative, right? So there's all these rules about how these variables fit together, but you can double check these rules, and I would have them on the equation sheet. Okay, so now this is fun. We're going to practice what happens to light rays when they go through a lens, right? So we're going to practice the rules and use it to identify images. Okay, so we can go through this relatively fast, but if I'm going too fast, you could just pause between each one. Okay, so where does the light ray end up? So notice that this is representing an object. So I have this orange object, which is represented by this arrow. This is the axis of my diagram. What would happen to the light beam once it intersects this lens? Okay, so it should be C, right? So light beams that go through the focal point will end up coming out the other side parallel to the axis of the lens. Okay, what about this one? Okay, so light beams that come in parallel should be extended out through this focal point. So I think the answer is C. Okay, what about this one? This one's the easy one. So when you go through the center of the lens, you should just go straight through. So the answer is C. Okay, so now I'm using those 3 light beams. And you can tell me now what kind of image is created. Is it real or inverted? Real or virtual? So because it's made from real light beams, it's going to be real. Is it upright or inverted? It's inverted. Right, so it's upside down. And then is it shrunken or enlarged? It's shrunken, right? So because the height is smaller, the image height is smaller than the object height, then you would say that it's shrunken. Okay, so if I was writing out what is the magnification of this image, I would say the image height is smaller and inverted. So the magnification would be less than 1 and negative, right? Okay, let's continue. So where does this light beam end up? Okay, so hopefully you said A. C. Right, so light beams that come in parallel, this is hard. So light beams that come in parallel have to go through the center, right? This focal point. Okay, let's do another one. Where does this light ray end up? Okay, so now this is a light ray that looks like it's coming from this focal point, So it should come out the other side parallel. So I think it's B. Okay. So now we have the purple ray is a light ray that just goes through the center. This red ray is a light ray that goes parallel and goes through the far focal point. The green one is a beam that looks like it came from the near focal point and comes out parallel. We trace backwards and find the intersection of all three. And now what kind of image is being produced? It's going to be virtual, upright, and enlarged. Right? Okay. Okay, let's try more. So now we have, the difference now is we have a concave lens, right? So notice how this is drawn as a concave lens. So now we have actually different rules for what happens to the light beams. Okay, so where does this light ray end up? Okay, hopefully you said A, right? So here I have a light beam that is starting out parallel. It's going to get diverged through this lens. At what angle does it come out? It comes out as if it came from this near focal point. What about now? So now I have a light beam that looks as if it's going towards the far focal point. Okay, hopefully you said B, right? And now we can combine together the purple ray that goes straight through, the green ray that I can trace backwards, and then this red ray that I can trace backwards. Where these rays intersect, I can put my object and my image, right? So the image is this yellow thing. Okay, so what kind of image is produced? So because it's created by the intersection of virtual rays, I would say this is a virtual image. It's definitely upright and it's shrunken, right? Okay, last practice. So now, same thing, but now we have an object that is on the inside of this focal point. Okay, so now we have a light beam that's coming from the object parallel. We would expect to use light ray A. Good. Now let's have one that looks as if it's a light beam that looks as if it's going towards this far focal point. So then we need beam B. And now we combine together all three and we find the intersection of those three rays. This gives us a virtual, upright, and shrunken image. Cool? Okay, so now let's practice using this thin lens equation. So it says I have a 2 centimeter tall object placed 15 centimeters to the right off of a converging lens. The lens has a focal length of 20 centimeters. Where is the image created by this lens? So now I know that I'm within the focal length of the lens. And so I know that we can calculate the image distance, right? So the focal length is 20 centimeters. So I would do 1 divided by 20, which is actually 0.05. The object distance is 15, so it's 1 divided by 15. So now I need to do 1 divided by 20 minus 1 divided by 15. So I'm going to punch that into my calculator. So I get negative 0.016. So now I need the inverse of that. So I'm going to take the inverse of that calculation, and I get 60. So negative 60 is my answer for DI. Okay, so what does it mean to have a negative image distance? It means that my image and my object are on the same side of the lens. So it says that my object is to the right of the converging lens. So that means that I would get an image 60 centimeters to the right. So I think my answer is B. Yeah, so I solve this equation for DI, I get minus 60, and so that means the answer is B. So if your answer had been positive 60, you could say that the answer was D. Okay. So now let's figure out what is the height of the image, right? So how tall is the image? So we know that the image distance is 60 and the object's distance is the image distance is 60, the object distance is 15. So 60 divided by 15, 60 divided by 15 is 4. But DI is negative, so it would actually end up being upright and 4 centimeters tall. Oh, sorry. No. That's the magnification. The magnification is 4, right? So if the object height is 2, I can solve for the image height, right? So I need 4 times 2, so it would end up being 8 centimeters. Right, so the magnification is minus DI over DO. It's also equal to HI over HO. I can solve this equation for HI, and I get HO is 2 centimeters, DI is minus 60, DO is 15. I can solve and get 8. Okay, an object is 5 centimeters in front of a diverging lens whose focal point is 10 centimeters from the lens. How far is the image from the lens? Okay, so here, because it says it's a diverging lens, it says the focal point is 10 centimeters, but that means that you would use a focal length of minus 10 centimeters, right? So because it's diverging, you would use minus 10, right? And then the other thing that you know is that the object is 5 centimeters, right? So I know DO is 5 and F is minus 10, and so I can solve this equation for DI. So why don't you try that on your own? Okay, if you're coming back, ready for the answer, I can solve this equation for DI, and then plug in the values, and I get minus 3.75. So I end up with an image that is on the same side of the lens as the object, and it's closer than the object to the lens. It says a real object is located a distance from a diverging lens that is twice the focal length of the lens. How far is the image from the lens? So it's saying that it's a diverging lens, so the focal length is negative, but that the object distance is twice the focal length. So DO is negative 2F, or you could think of F as negative 1/2 DO, right? And you could plug into this equation and solve for DI. So I think you end up getting that DI is F, right? Because I need, or minus F. How far is the image from the lens? It's going to be minus F, because here I would have No, it's hard to do it in your head. I think you need to do this on paper and calculate the algebra. Okay, so I get 2/3 f. So it's always easier to kind of invert this thin lens equation and solve it for DI. So just be very careful because it's a matter of adding together fractions and then flipping it upside down, right? So it's a little bit like our equivalent resistance formula. Okay, and here's another example where we have an object. A real image is located 36 centimeters from a converging lens. If the object is 12 centimeters from the lens, what is the focal length of the lens? What is the magnification of the object? Can you determine the height of the object? So here's some practice where you need to answer a bunch of questions about an image that's being created. So use these formulas for the thin lens equation and the magnification and try to calculate the answer. Okay, and here we go. This is the answer. I'm not going to talk through it. So the last topic that I want to discuss is spherical mirrors. This is my favorite picture. It's a drawing made by M.C. Escher of, it's a self-portrait in a spherical mirror. Okay, so for a mirror, we would definitely expect sorry about that. For a mirror, we would expect that there could not be light rays or real light rays on the other side of the mirror, right? Because for a mirror, you're going to get reflection backwards. So let's just talk about what happens to light beams. What are the rules that we need for convex and concave mirrors? And so for a spherical mirror, you would identify 2 points that are relevant. One would be the center of the circle that's created by that sphere, and then the other is the focal point. So it's going to turn out actually that this focal point is half the distance of the center. Okay, but the rules are for a mirror that light rays that strike the center of the mirror get reflected symmetrically, and this is what I mean. So if I have a light beam that hits directly on the axis of the spherical mirror, it's just going to bounce off exactly like it would for a flat mirror, right? Using the angle, the law of reflection. So here I have a concave mirror, so the light is coming in on this side of the mirror. Here I have a convex mirror, and so light is bouncing off of the outside of the sphere. So again, I have a light beam bouncing off of the center axis. Light rays that are parallel will go through the focal point. So if I have a light beam that comes in parallel, it's going to reflect off of the side of this this mirror, and it will bounce off into the focal point. I'm just going to pause for a second. Okay, I'm back. So light rays that are parallel will go through the focal point. Let's see what that looks like. So I need a light ray coming in parallel, bouncing off through the focal point. And again, here, because a light ray can't get transmitted through the focal point, it will actually just bounce off as if it came from the focal point of this convex lens, right? So anytime you're unable to do something with a light beam, you want to backtrack and obey that rule anyways. So here it's just saying that if you come in parallel, you should bounce off as if you came from the focal point. Rays that go through the focal point become parallel. So this is the reverse of that previous rule. So it's saying if I have a light beam that goes through the focal point, it's going to bounce off parallel to the axis of the mirror. So here I have a light beam that looks as if it's coming towards this focal point. It's going to bounce off parallel to the axis. So this rule is actually the reverse of the previous rule. Okay, there's one final rule for spherical lenses, and it says that a ray that bounces through the center will bounce backwards without bending. Right, so if I have a beam that goes through the center of the circle, it's essentially the same as shining a light directly towards a flat mirror. It's just going to bounce back perfectly. Okay, so now we can do this ray tracing practice for a spherical lens, or spherical mirror, sorry. Okay, where would this light ray end up? So now I have light coming from my object. It's coming in parallel. It's going to go through the focal point. So we need ray B. What about this one? Okay, hopefully you said A is the right answer. And now here I have all four light rays. Right, so I have the one that's parallel, goes through the focal point. The one that comes through and bounces off of the axis comes back at the same angle. The one that goes through the center just comes back the way that it was supposed to. And then this one is coming in through the focal point and bouncing off parallel. So actually all four light beams intersect at a particular point. So what kind of image is produced in this case? Sorry. Okay, hopefully you said that this is a real image. It's inverted and shrunken. Good. So here's a representation of what just happened. Same idea. So now let's try one more practice. So now I have an object that is in between the center and the focal point. So I would expect a light beam that comes off parallel to bounce through the focal point. I would expect a light beam that goes through the focal point to bounce off parallel. And this is what it would look like if you drew all four light beams. They would all intersect at the same point. So what kind of image is created here? Okay, this is a real image, inverted and enlarged, right? Okay, so now we have an object that is closer to the mirror than the focal point. So we can draw a beam that comes out parallel from that object, and it should go through the focal point, so B. We have a light beam that looks as if it came from the focal point. It should come out as light beam A. And now this is what happens if you draw all four light beams. So here I have the blue beam is the one that's bouncing off of the center. The red beam is going parallel and then bouncing back through the focal point. The green beam is coming out away from the focal point and comes out parallel. And then this purple beam is just bouncing. It looks like it came from the center. It's just bouncing directly back. So do you see how none of these beams would ever intersect? So then the only way to create an intersection is to trace these beams backwards. And notice how here I obviously made a mistake somewhere because not all of my beams intersect perfectly. So I think I made a mistake somehow, but I would expect that this would be the image distance where most of my beams are located. So let's talk about what kind of image is produced in this case. So because it's the intersection of virtual light beams, I would say that this is a virtual image. It's definitely upright and it's enlarged. Okay, so here these are the three examples of placing an object outside of the center point, between the center point and the focal point, and then inside of the focal point, and the types of images that are produced in each case. Okay, I don't think I have examples of the other type, a convex mirror, but a convex mirror will always create a virtual, upright, and reduced in size image. So there's only one kind of image created from a convex lens. So one example of this would be, like a funhouse mirror. If you had a convex lens, then you would look shrunken and smaller. If you had a concave lens, you might look bigger. But one example of a convex mirror is actually the mirror in your side view. And so that's why it says objects in mirror are closer than they appear. It's because the image is actually closer to the mirror than the actual object creating the image. Does that make sense? Closer than they appear. Then wouldn't that mean that it's like the other way around? I don't know. Okay, so the equations for mirrors are almost identical to the equations for lenses. For spherical mirrors are, similar to the ones for spherical lens. The focal point is actually half of the radius of curvature of the lens. So here's an example problem for spherical lenses. You can ignore the fact that it says homework 3. That's for a different class. But here you can practice an example problem using spherical mirrors. So it says you place the object on the axis 44.5 centimeters in front of it and discover that the mirror creates a virtual image 16 centimeters from the mirror. So because it's virtual and it's on the other side of the mirror, we would say that this is a negative value. So images are always negative when they're virtual. Calculate the mirror's radius of curvature. So you could solve for the focal length by plugging in these values into this equation and then solving for f. The radius of curvature would be double the focal length. And then it's asking, is the mirror concave or convex? A concave mirror would have a positive focal length and a convex would have a negative focal length. Okay, I think that that is enough. I actually also have slides here for using ray tracing to describe how vision works and how multi-lens systems work. I'm just going to leave them in the slides, but we're not going to discuss them, and they won't be a part of the homework or the quizzes or exams. So this is the end of lecture 9. Okay, I'm going to stop.